Next, exercise 3. Here we have a graph G that contains a cycle C such that there are two vertices in C that are joined by a path of length at least k, and that path of course is a path in G. Then we have to show that G contains a cycle whose length is at least square root of k, and also is this the best possible bound. So let's see the solution. In the solution, we are first of all going to consider those vertices where this path that the author is talking about intersects C. So let these vertices be V1, V2 up to Vt. Okay. Let the path P, let's give it a name P, of length at least k intersect. I'm not quite sure if I should use this word here, but you understand what I'm trying to say, right? But most of the things in graph theory, most of the terms and definitions are highly natural. So in that sense, I am using this. Intersect C, the cycle C, at the vertices V1, V2 and so on up to Vt. So the situation is like this, of course. Say this is your C, some cycle. How many vertices there are in this cycle, we don't know that. Okay. But we know one thing, that these are the vertices on C at which that path intersects C. So say this is V1, this is V2, and this is say Vt, this vertex. So the path of course starts at V1 and then it reaches V2 and then again it leaves the cycle and goes to V3, wherever that is, and like that it ultimately eventually reaches Vt. You may think that these intermediate portions of the path, so this is our path P, this wavy path. You may think that these intermediate portions of the path between the two consecutive VIs may also intersect C, but that is not going to happen, because had that been the case, that point of intersection would already have accounted in this list, right? But that's not the case. So these intermediate portions are entirely outside of C, right? So this is pretty much the situation. Now there is a case in which we need not do anything practically. If it happens that the number of these common vertices, that is T, itself is at least square root of k, then what happens? Now if T is at least square root of k, so then likely the cycle has more vertices than these vertices, or maybe these are only the vertices in the cycle, but in any case the order of C, that is the number of vertices of C, is at least T. So if T is at least square root of K, then the order of this cycle, or in other words, which is also the same as the length of the cycle, C itself is at least root K. And that's it. Then we have found one such cycle in G. Then the number of vertices of C is at least root K, and so C is a cycle in G of length at least square root of K, and the thing ends here. But that happens only if we have this. So let T be strictly less than the square root of K. Now you can see that there are these intermediate portions, right? The portions of the path P between two consecutive VIs. Now what about the lengths of these portions? We are now going to suppose something about the lengths of these portions. Suppose that the parts of P between Vi and Vi plus 1, or because we are going to vary I, so let me call it part. Suppose that the part of P between Vi and Vi plus 1 has fewer than root K edges. For all possible lines. What happens if that is our supposition? So how shall we have to vary I? I will vary in this range T minus 1, because we are mentioning Vi plus 1, so I can have at most this value T minus 1. So what we have supposed here is that all these intermediate parts of P in between these consecutive VIs, all of them have fewer than square root of K edges. That means the length of each one of them is less than square root of K. But then taking the sum of their lengths gives us the length of P. But then the length of P is less than the sum of length of P is not less than the sum of the lengths of these parts. It is equal to the sum of the lengths of these parts. But the length of each part is less than root K. So that sum itself is less than that many root K's as many parts we have. How many parts do we have? T minus 1 is less than T minus 1 times root K, okay, and that of course is less than T times root K, obviously, because P minus 1 is less than T and root K is a positive real number. That's why we have this inequality. But now note that t itself is less than square root of k, because this is our starting condition in this part of the solution. So this is less than square root of k times square root of k. Again, you can multiply on both sides of this inequality by square root of k, because that's a positive real number, and have this inequality. But that is this. So what we have concluded, that the length of p is less than k. But that directly contradicts the hypothesis that p is a path joining v1 and vt whose length is at least k, that is greater than or equal to k. But here we have found exactly the opposite thing. But this contradicts the hypothesis that, let me just keep the diagram. That the length of p is at least k. So that means our supposition is wrong. So our supposition is wrong, and as a consequence, the part of the path p between vi and vi plus 1 is at least square root of k. So what was our supposition? We supposed that for all such i's, the part of p between vi and vi plus 1 has length less than square root of k, which led to this contradiction. So that means there should be at least one portion whose length is greater than or equal to the square root of k, right? That's what we have written. For some or for at least one, same meaning, for some I in this range. But then what? Say this is vi plus 1, just for the sake of understanding. Suppose this is vi plus 1 and this is vi. So now what we have known, that the length of this part is greater than or equal to square root of k, but it's only a path between vi and vi plus 1. Now we want to create a cycle using this path, and of course something else, and that something else you can either choose to be this path joining vi and vi plus 1, or this path joining vi and vi plus 1. That is, along the cycle you have two paths joining vi and vi plus 1. You can decide to combine any one of them along with this part of p to create a cycle, and the length of that cycle of course will be greater than or equal to root k. So let's write that in words. Hence the cycle obtained by taking the union of the part of P between Vi and Vi plus 1 and any one of the two paths along the cycle C joining Vi and Vi plus 1. So this is the part of P and any one of these two paths. One of them is this and the other one is this. If we take the union of these two things, then we are getting another cycle, and that cycle has length at least square root of k. Well, you can clearly see that the length is actually greater than that, because this part itself is at least square root of k, but you have something else also, no? And that something else in the least possible case is one extra h, right? Yeah, so actually should I write it that way? Actually the length will be at least square root of k plus 1 because of this, and that answers the second part of the exercise. The author has asked, is square root of k the best possible bound? No, it is not. At least square root of k plus 1. Hence, and this 1, of course, if you want to write in words the justification, the 1 appears because of that other part, whether it be this path or this path. That path has length at least 1, so that's why at least square root of k plus at least 1. Hence, root k is not the best possible bound, and that is the solution. Let's see another one, the fourth one. The fourth one comes with a minus superscript, which means it is very simple. It's supposed to be simple. Is the bound, but the ones with a plus superscript are supposed to be somewhat complicated. We will come across them. Is the bound in proposition 132 best possible? Well, that requires us to first of all recall the statement of this proposition, and then we will have to also understand what it is that we mean by best possible, and then we have to answer the exercise. This proposition is about an upper bound for the girth of a graph, and the proposition, let's recall the statement. For, I may not be writing the exact statement, but I may not be writing the exact sentence, but this is the statement. For every graph G with a cycle, that means there is at least one cycle in the graph. It's not an acyclic graph, it's not a forest. The girth of G is at most 2 times the diameter of G plus 1. So for such a graph which is not acyclic, which has at least one cycle, the girth cannot exceed this bound, that is 2 times the diameter of G plus 1. Now what is this best possible? Well, you can see that this is an upper bound for the girth of G. It's not a fixed number, of course, it changes as G changes because the diameter changes. Well, the thing here is that if it is not best possible, what does that mean? It means that you can modify this entire statement itself by replacing this bound with a smaller upper bound. If that is possible, then this is not the best bound. But actually, you cannot replace it with a smaller upper bound because of this graph. So it is the best possible. Did I just say that it's not the best possible? Anyway, so the thing here is that it is the best possible. We cannot improve it any further. So I write yes. And the justification for that is, consider the cycle C3, that is your triangle. Now for this graph, what is the girth? Girth is the length of the smallest cycle. It has only one cycle and its length is 3. This is equal to 3. 3 is 2 times 1 plus 1. But note that 1 is actually the diameter of C3. That's because that is the maximum distance between any two vertices of this graph. So this example shows that in general we cannot reduce it any further, right? So that is why this is the best possible bound. And let me just end the video here itself. We are going to, of course, solve the other exercises that come next, as many as we can. And last Saturday I wasn't able to film the thing, so tomorrow we are going to solve group theory problems from Gallian's algebra. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.